Okay everyone, welcome back. Today we are going to talk about the next section, section 1.5, that is about flow rate. Okay, the two most important properties in this particular topic is your mass flow rate and your volume flow rate. Okay, mass flow rate is looking at how many kilograms of fluid, okay, flowing past a certain point. So of course the time factor is there, and you also have the mass factor there. So the units for mass flow rate is kilograms per second. This will be denoted by m dot. Okay, mass for m dot, indicating the time factor over here, mass per second. Volume flow rate, on the other hand, is talking about how many meter cube, because volume, you know, the SI unit is meter cube, and so the unit is meter cube over a period of time, so it is meter cube per second, and we denote it by the letter Q, capital Q. For this chapter, Q will be volume flow rate. So how do you visualize this? Let's give a very simple example. Let's look at example 1-11, right? So if you have done household chores, mopped your house floor before, you should know that when you turn on the tap and water fills up your pail, right? And you wait for a certain time, and the pail fills up, and then you turn off the tap. So this is what exactly is happening. Okay, the water from the pipe or the tap fills a container of 30 liters in 4 minutes. Okay, so your key numbers are 30 liters and 4 minutes, right? So the conversion between liters to meter cube is this. 1 liter is 0.001 meter cube. So 30 liters is 0.03 meter cube. So this is in SI units already. And what about 4 minutes? 4 minutes is 4 times 60 seconds, which will give you 240 seconds. Alright, so if you look at this, the flow comes out, okay, filling the 0.03 meter cube in 240 seconds. So I can find, this is volume, I can find the volume flow rate. The volume in this amount of time. Okay, let me just get my calculator. And it will give you 0.000125 meter cube per second, okay, which is also equals to 1.25 times 10 to the power of minus 4 meter cube per second. Okay, and the question asks for liters per second. So again, converting from meter cube to liters is multiplied by 1000. So it will also be 0.125 liters per second. Okay, so this is how you see it. So the tap, the water that flows out from the tap, is flowing out at 0.125 liters every second. That is your volume flow rate. So if you want to look at mass flow rate, how exactly do this and this connect? You know, right? Last time, mass is equals to density times volume. So it doesn't matter whether there is a time factor inside, it remains the same. Your mass flow rate will have to be density multiplied by your volume flow rate. So it is the same idea. So for this case, since we are looking at water, so the mass flow rate through this pipe, right, will be density of water times the volume flow rate that you just found out. except now that you don't use liters per second, you use meter cube per second. So 1000 times 1.25 10 to the power minus 4 meter cube per second. This will give me 0.125 kilograms per second. Okay, so this is how you convert. This is how you get mass flow rate from volume flow rate. So now I'm going to take this one step further. If we go to page 24, okay, this is more related to volume flow rate. So volume flow rate, you know, is volume over time. Okay, now I want you to imagine, okay, I'm not sure if you've played this before, but if you don't, go and search YouTube for this product called Play-Doh. It is essentially a plasticine. Okay, and one of the very popular tools that inside this plasticine toy is whereby you put your plasticine, okay, into a box, into a kind of container, and there is a hole here. There's a hole. Okay, and what you do is you have a piston of sorts, right, or a lever, and you push this plasticine through the hole. Okay, and what comes out is one long tube of plasticine. Okay, if you know what I'm talking about, I hope so. So this tube of plasticine will come out, and then the shape of this tube, right, is the same as the shape of the hole. Okay, so now imagine that I'm pushing out through a diameter, this is just an example, of 5 cm. Okay, and I am squeezing out plasticine from this side. Right, so naturally the plasticine will come out in this form, in this shape. So this will also be 5 centimeters. Alright, so for example, if we manage to squeeze a tube that is 20 cm long, okay, over a time of 10 seconds, let's say 10 seconds, what do you think is the equivalent flow rate? Okay, so basically you just find this entire volume that is being squeezed out, and this is the volume created over a span of 10 seconds. Right, so let's try this. Sorry, let's just find the volume first. This is cross-sectional area. Okay, so volume is cross-section area multiplied by length, which is the length of this tube. So the cross-section area is a circle of diameter 5 cm, right? So the formula of circle is pi d square over 4, and the length is 20 centimeters. So let's convert to meters. You get 0.2 meters. Okay, so pi d, you should use meters as well, becomes 0.05 meters square over 4 times 0.2. So the volume is 3.93 times 10 to the power minus 4 meter cube. This is the volume that is produced over 10 seconds. So my volume flow rate is volume over 10 seconds, which will give me 3.93 times 10 to the power minus 5 meter cube per second. So this is the so-called flow rate. Okay, now imagine if this is not Play-Doh. This is not plasticine, but this is a certain fluid. This is water. Okay, the water will also come out in the same fashion, and the volume can be calculated using this same method exactly, right? And this is how you imagine the flow rate to behave like. So, to summarize, so my volume flow rate is volume divided by time. Okay, but you should also see that the volume, like I say, is cross-section area times length over time. Okay, and this cross-sectional area is, let's denote it with A by A times length L over time T. Okay, you will realize that there's this length over time. Okay, in fact, length over time is also velocity. Okay, so in fact, Q is area times velocity of the flow. Okay, can you see that? It is 20, for this case, the Play-Doh is going at 20 centimeters per 10 seconds, which is 2 centimeters per second. That is the velocity of the so-called flow. Okay, so therefore UQ equals to UA, and that is a formula expressed in page 24.